dia. Vamos começar então com o segundo dia. For those of you who were not here yesterday, I would like to introduce you Dr. Sebastian V. Massimini, if I speak correctly. He is currently a senior principal engineer at the MIT Corporation Center for Advanced Aviation System Development in Virginia. He is a project manager and research analyst in the field of navigation and surveillance for civil airports and air traffic control architecture, including the use of satellite navigation systems and future surveillance techniques in the terminal and en route environment, both in the U.S. and internationally. He also does research on approaches and departures at multiple parallel runways and assessment of airport safety standards. Dr. Massimini is also an associate fellow of the American Institute of Aeronautics and Astronautics. He received a Doctor of Science in Operations Research from the George Washington University, Master of Science degrees in Mathematics, and also in Industrial System Analysis from the University of Memphis, and a Bachelor of Mechanical Engineering from the Georgia Institute of Technology. Dr. Massimini retired in 1990 as a lieutenant colonel from the U.S. Marine Corps, where he flew the A-Force Skyhawk and other jet aircraft, including several hundred combat missions in Vietnam. He has worked as a tour guide at the National Air and Space Museum in Washington and at Dulles Airport since 2005. He currently lives on an airport in Maryland and flies his full and checked aircraft from the grass runway in the backyard, including commuting to the museum location. He is also engaged in building a motorized glider and is a current airplane and instrument flight instructor. So without further ado, I would like to...
Okay.
Thank you.
So, welcome. Again, I said yesterday, I'm a gringo here, so I don't speak very many languages. I do speak Spanish, but not Portuguese. So I will try to talk slowly. If you don't understand something, just let me know and I'll try to repeat it. And if you have questions, just ask. It's okay. We can either do questions at the end or if something comes up, so just stop me and ask. I know you will stop me right away, so that's okay. For those who were here yesterday, this briefing is a little different presentation, but I did use some of the same slides, so you'll see some of the same slides today, but talking about a little bit different aspect of those slides. Okay. And like I said yesterday, the presentation is here. I believe that Milton is putting it on YouTube, so you can listen to it again if you like. But the presentation does not contain everything I say, so a little caution there on using the slides directly. And again, talk a little bit about MITRE. We're principally a research organization. The whole company is about 8,000 people that works for very many parts of the U.S. government and foreign governments. All of our work we call is public interest. So we do not sell software, we do not sell equipment. We do develop software, but normally we give it away. We do patent technology, but normally we do not make any money from the patent. So for the example I use a lot is GPS. We have many patents on the GPS technology, but they were patented to make sure that no commercial organization patented the technology and started charging people for it. So many patents we have, but we will give a license. It's called a royalty-free patent, so nobody. We don't have commercial links. We don't generally work for commercial companies. There's a couple of, I work for a commercial company in Argentina. Aeropuertos Argentina goes meeting. And they're a commercial company that does airport concessions. And we have actually permission from the regulator in Argentina to work for them. So we generally only work for governments governments or government organizations. And again, we don't provide any software or equipment. And the part of mine that I work in, which is about 800 people, works with civil aviation. Most of that is with the United States Federal Aviation Administration, but some is with foreign governments. And I personally work in many countries around the world, mostly on area navigation, but also on airports and airport development. He mentioned this is my house, and this is my airplane's house, and it's right underneath. And this area right here is the grass runway. My neighbors and I have the runway, so I go flying whenever I like. And this is the inside of my airplane. This is an SBAS, for in the U.S. it's WAS, and this allows me to go almost anywhere I want and land almost anywhere I want. And then this is an ADS-B transmitter, so that the GPS position from the WAS navigator is transmitted out to air traffic control. Also, I can receive traffic information and it displays on this display. So that's a nice thing. We'll talk a little bit about that because it relates to air traffic management. Okay, so what's the real relationship between GNSS and air traffic management? Okay, and I would say that there isn't any. GNSS, like I said, don't leave. I got more to say. Okay. There's really no direct relationship between the GPS satellites and the GPS signals and what is done for air traffic management to manage the flow of traffic. If you look at the air traffic automation that's in our air traffic control systems, there are GPS timing receivers in there. But we have looked at that, and those systems are fairly robust to having some time errors in general. That's not true of all automation systems, but that's true of the U.S. automation systems. It turns out electrical grids and cellular telephones are very sensitive to time losses. As a matter of fact, about 7 or 8 years ago, we had an interference event in California, in San Diego. And I'm not sure that event wasn't deliberate, but it was at least an event where GPS was lost in the San Diego area. It was interfered with. Nearly every cellular telephone in the area went down. They were all lost. Except, I believe, Sprint network was robust to it. They didn't have a receiver there. So electrical grids and cellular telephones are very much connected to GNSS and have big problems. This is a big concern in the U.S. I don't know if it's in Brazil, but certain interference could bring down parts of the electrical grid and parts of our communication grid. But that's not the case with air traffic management. However, the GNSS and the way we use GNSS is a major part of air traffic management. And there's two big parts of this. And I tried to reduce the number of acronyms in this briefing. I believe that the air traffic management folks have a big crank, and they crank it out, and they crank out acronyms. And I can't keep track of them all either, so I tried to not use as many acronyms. But the major things for air traffic management are trajectory-based operations. And we're going to talk about how those are used with GNSS capabilities to regulate the flow of traffic to and from our airports. And then also interval management. This is something that's fairly new and it's not implemented in many places yet, but it is a big use of GPS and hopefully in the future for traffic flow management. Just a couple of review. I used some of these slides yesterday. So the big enablers for GNSS for trajectory-based operations and interval management are area navigation and RNP. This gives you precise horizontal navigation. navigation, okay? And in the future, we don't use this right now, but also precise vertical navigation. So right now, if an aircraft is leaving, say, 35,000 feet, coming into an airport, the horizontal navigation can be controlled by GPS. We don't really use the vertical navigation. We have restrictions on where the aircraft can be at certain points, and I'll show you some of those. In the future, we would like to have that path be defined all the way down to the runway. That's not happening quite yet. Also, one of the points, it's nice to have precise navigation, but air traffic control needs to know where the airplane is. So if you have radar, that's a good way to know. But in many places, we don't have radar. Of course, Brazil has many aircraft coming through the Atlantic and coming into the areas, and you don't find out where they are until they're close to land, unless you have automatic dependent surveillance, which is where the aircraft transmits its position. There's two basic types of automatic dependent surveillance of ADS. There's ADS contract, which is called ADS A or C. So I don't know. Boeing calls it one thing, Airbus calls it another. I don't know why they can't use the same name. But one is ADS A and ADS C, but it's the same thing. And the position of the aircraft is set up to a geosynchronous satellite, a communication satellite, and sent down to air traffic control. Maybe once every 5 minutes. ADS broadcast sends out usually every 1 second, and it goes to ground stations. And there's also a remote area. There may be a space-based ADS-B in the next few years. That's just being launched. We'll talk about that. Aircraft avionics in the airplane uses those positions along with air traffic control to provide the basis for trajectory operations. Okay, performance-based navigation. Like I said, the big deals here are RNAV and RNP. And RNAV, in the past, we used to go between ground stations to go from an origin to a destination. Now we use area navigation routes, which we just have geo-reference points, and we fly along those geo-reference points. That's RNAV, area navigation. For RNP, it's just an enhancement of that allows a little bit more control and also allows curved paths. Okay, so we use the terms RNAV and RNP considerably in our discussions of trajectory-based operations. And like I said, automatic dependent surveillance is where the aircraft sends its position to other aircraft and down to air traffic control. All right, trajectory-based operations. This is most of the stuff being done for traffic flow management, principally in the U.S., but it's also being done in other spots. And what you've got is a number of programs that are called time-based management. And I'm sorry again, we have all of these acronyms again, TBM, TBM, TBO. But what we're doing here is sequencing our aircraft so that they depart at a time, not all at the same time, and they get to their destinations, not all at the same time. And of course, the aircraft, when they depart, go to different airports, and they come in from different airports to land. So this is all the metering. We do that when the aircraft arrive. We do it on the surface of the airport. We do it in the terminal area when they're departing. And also, if necessary, we hold aircraft on the ground to keep them from departing so that when they get to their destination airport, they have a place to land, or time to land. The way we do that is with area navigation and required navigation performance, RNP and RNAV. And the flight management systems in our airline aircraft work navigator. I can go anywhere I want, but I can't interact with air traffic control. So for small airplanes like myself, this is all done manually, not automatic. But what we're trying to get is for our larger airliner aircraft to be able to sequence things automatically. We also try to have optimal profile descents. So what the pilots would like to do is start maybe 200 miles from the airport at, say, 35,000 feet. They want to pull the power back all the way to idle, and they want to use a minimum power setting all the way down until they land. That's really hard because every airplane is a little bit different. If an airplane is heavier or lighter, even if they're the same kind of aircraft, they fly a little differently. If the wind is stronger on one day than another day, it's different. So, but we try to do these optimal profile descents. And then there's a lot of other technology that comes in that I'm not going to talk about today. Datacom. If we can exchange data automatically, then that's much faster than trying to do it by voice or other method. We do that what we call in the U.S. System-wide Information Management, SWIM, more acronyms. So we try to exchange data and keep track of those data. And we also want it so that an aircraft taking off, for example, from New York City that has data, and he's going to Los Angeles, that Los Angeles can get those data about that aircraft. And then this is all advanced data exchange. Aviation weather. Weather still screws us up, and it's going to continue. We have to remember that God still runs this place, right? So if he does a thunderstorm, and we can't do much about it. But we try to at least predict the weather better. Our famous humorist and author was a man named Mark Twain. If you read English literature, he's a very famous one. And he was a very funny man. And one of his sayings was, prediction is very difficult, especially when predicting the future. Right? So this is very true. So we're trying to do better on weather, but we're not the ones who control the weather. Okay. So again, the time-based management is this is the key to these trajectory operations. And what we really have is what is the trajectory of the aircraft? So what's the route of the aircraft? What's its arrival time over certain important points, which we call metering points? And how do we exchange that information between the aircraft and the ground and the ground and the aircraft? And this is really where the use of RNAV and direct routes are key. And of course, those are enabled by GPS or GNSS. And the important thing, and what has to be done, and this is really the hard part, is you have to manage in a very broad technique to catch people from taking off and all the way to their landing, and trying to sequence them so that this may be several hours of flight here, and you have to deal with weather on the way to get here and where everybody doesn't arrive at the same time. So again, this is trajectory, time-based management plus. All right, let's see. Just ignore it. All right, that's all I did. Okay. And it's a combination of this time-based metering and PPM, which is our neighborhood. Okay, in the U.S., we're actually getting rid of routes. This is what the U.S. looks like today. There's actually green routes, and if you see there's red routes in here. The red routes are high altitude routes, above 18,000 feet. The green routes are below. We're actually these routes are based on VORs, on ground-based NavAers, and we're getting rid of many of those VORs. And in about 5 years, this is what the routes are going to look like. So you can see we've just gotten rid of almost all of the routes in the central and eastern United States. The reason that many of these routes are staying is they're in the mountains. So that's the mountainous area for the U.S. So we kept some routes in the mountainous areas and some of the ones. So what are we doing? Well, we're doing area navigation routes. I showed this slide yesterday. The black routes here are the green ones in the other thing. They're VOR-based routes. And the blue routes are actually area navigation routes. In this particular case, this is the airport in Charlotte, North Carolina. And you can see the black route runs right over the airport. And they don't like that. They do not like you flying right through the middle of their airspace when they're doing landings and takeoffs. So they designed area navigation routes that go around the airport. That's very common now in the U.S. Mostly we're trying to just let people fly direct. Okay, but in cases like this where you have very busy airspace, we want to route them around the airspace so we come up with routes. Okay. Now I mentioned yesterday this is the airport where my daughter lives close to, so I fly down here all the time from my airport. Arrival procedures, again, I showed this slide yesterday. This is the Houston airport here, and this is the arrival procedure. And I mentioned this yesterday, this is very difficult. Each of these is a waypoint. So that when you're coming in from the west, you fly waypoint to waypoint and down to the runway. And each of these is an altitude restriction. So it really is kind of hard to fly. So as you're coming in, this is very nice for air traffic control because everybody flies this same route. But it's very hard for pilots. With the airliners though, many of the airliners can do this on automatic pilot, and that's good. Some of them can't. So this is a thing we're still working on. They've tried to make this as a optimal profile descent, where the pilot can start way back here and start down and only make minimal power corrections. But again, it's still very difficult.